Oh, so if I want percentage by mass, I need grams over grams, grams of KNO3 over grams total, which is solution. So I need to go moles to grams, liters to grams. And so that's the strategy here, and then multiply by 100%. So I need the molar mass of KNO3. Molar mass I just looked up on Wikipedia here. Molar mass from Wikipedia is 101.10. And so just type that, use that molar mass. I don't have to calculate it. It's 101.10 grams of KNO3 per mole of KNO3. And so I'm just starting off with the molarity that was given here. And so that gives me grams of KNO3 on the top. Now I got to get rid of liters of solution and get grams. And so I'm going to go from liters to milliliters. And so 1 liter is 1,000 milliliters. And so now I have milliliters of solution. And then I'm going to use this. For every milliliter of solution, I have 1.15 grams of solution. There. And so now I have grams of KNO3 on the top, grams of solution on the bottom, and just multiply by 100%. And that should give it to us, the answer here. So that's going to be 3.3 times 101.1 divided by 1,000 divided by 1.15. Times 100, 29.01%. We're allowed 3 sig figs, so 29.0%. See what they got. Yeah, 29.0% KNO3. Okay, let's move on. Calculate the molal concentration. All right, molal is not one of those common units. Molality, but it's useful for collective properties. And so molality is moles per kilogram of solvent. And so we want the molal concentration, 44.9 grams of naphthalene and 175 grams of benzene. And so the solute's 44.9 grams. And so here, what we're going to do is we're going to go from grams to moles. So we got 44.9 grams of naphthalene. Naphthalene, I'll just call it this, NAPTH. And then it's per kilogram of solvent, but we have grams of solvent. So this is the solvent. It's just solvent, not solution. And so we're going to leave it as grams of benzene. Because molality is defined as moles of solute per kilogram of solvent, not solution, just solvent. And so this is the solvent here. And so I need to go grams to moles. So I need the molar mass of naphthalene, and then I need to convert grams into kilograms, and then I'm done. And so that's what should have been done here. Let's take a look. And so they want grams to moles, and then to go from grams to kilograms. So they take the moles divided by the grams here of benzene and convert that to kilograms of benzene. So it's 2.00 molal. Essentially, that's what they did. But I just set it up as 1. Diethylamine is highly soluble in ethanol. Calculate the number of grams of diethylamine that would be dissolved in 4.00 times 10 squared grams of ethanol to produce 4.70 molal diethylamine. Okay, so 4.0 molal, we have to know what that means. That means 4.0 moles of diethylamine, we'll call it DEA, per kilogram of solvent. The solvent's ethanol. And so ETOH we'll use for ethanol. And that's what this means here. So what we have is we have 4.00 times 10 squared grams of ETOH. And so we need to go from grams of ETH to kilograms of E2H. And then kilograms of E2H, we can go to moles of DEA, moles of DEA. And then from moles of DEA, we'll go to grams of DEA using the molar mass. So I'll have to look up the molar mass of diethylamine later. But we can find it in this problem here, or calculate it. And so they're going from grams of ethanol to kilograms of ethanol, kilograms of ethanol to moles of diethylamine to grams using the molar mass. And that gives it to us here. How many milliliters of water are needed to dissolve 97.7 milligrams of sodium chloride in the preparation of a 2.80 times 10 to the minus 3 mol solution? So we're going to go from milligrams of sodium chloride to grams of sodium chloride, then grams of sodium chloride to moles of sodium chloride, moles of sodium chloride to kilograms of water to grams of water to milliliters of water. And so milligrams of sodium chloride to grams of sodium chloride to moles of sodium chloride. Then we're going to use the molality here. And so molality will allow us to convert moles to kilograms of solvent. The solvent in this case is water. We'll go from kilograms of water to grams of water to milliliters of water. And that's what we need there. So this is a dimensional analysis here. Let's skip this one. All right, equivalence we skipped. We skipped this unit here. So we'll skip that. We're going to skip these problems here. What is the molarity of acetic acid solution of 45.0 milliliters of 17 molar acetic acid diluted to 1.5 liters? And so this is a solution dilution. And so we'll need the solution dilution equation. Solution dilution equation, there are different forms. I just use this one. M1 V1 is equal to M2 V2. And so what we want is we want the molarity, M2. M2, it doesn't have to be molarity, it just has to be concentration. So another variation of C1V1 is equal to C2V2, concentration. Or you could do initial, MI, BI is equal to MF, VF, final, doesn't matter. And so M2 is equal to V1 over V2. This is, we call the dilution factor, I call the dilution factor times M1. So what is the dilution factor here? 45 is diluted to 1.5 liters. So we're going from 45.0 to 1,500 milliliters. So it's a 45 milliliter to 1,500 milliliter dilution. So it's a pretty big dilution of 17 molar. 17 molar is very concentrated acetic acid. Let's see what they did. So here they have the dilution, except, it's got to be the same units. It's a 45 to 1,500 dilution. So 45 to 1,500 dilution of 17 molar. 45 to 1,500 dilution of 17 molar is 0.51 molar, 10. How many milliliters of concentrated nitric acid, 16 molar, will you use to prepare 7.5 times 10 squared milliliters of 0.69 molar HNO3. So this is the concentrated stuff. And so we're solving for V1 in this particular case. And so we'll call that V1. This is M1. And then this will be V2, the dilute stuff, and this will be M2. So if we solve the solution dilution equation for V1, V1 is going to equal M2 over M1 times V2. And so M2 is 0.69 molar. M1 is 16 molar, so molar cancels out. And then V2 is 750 milliliters. milliliters. So multiply that out, you know. So it's 0.69 over 16 times 750 milliliters is 32 milliliters. Yeah. Calculate the volume of 18 molar. Okay, so this is the concentrated stuff, so solution dilution again. And so this is going to be M1, and this is going to be V1. This is going to be V2. This is going to be M2. So V1 is going to equal M2 over M1 times V2. So M2 is 2.9. Oops, this is normality. I didn't notice that. Normality and equivalence skip that. And so we're going to not do 87. Normality is related to equivalence, and we don't really need to cover that for this class. Even in Chem 1A, we skip normality too. I usually skip it. Normality is used a lot if you do a lot of titrations, but normality is easy to pick up once you figure it out the rest. So initially, we don't need it. If you do need it, it's pretty easy to figure. It's just don't have enough time to cover everything. 89, calculate the normality. So again, this is another normality problem. Normality is equivalence per liter of solution. So forget that. Normality, forget that. All right, calculate the mass in grams of magnesium hydroxide that will precipitate from 25.0 milliliters, 0.398 molar magnesium chloride by the addition of excess sodium hydroxide solution. So this is stoichiometry problem. So stoichiometry, yes, we do need that. Solution stoichiometry is very important. And so magnesium hydroxide precipitate. This is going to be precipitated from magnesium chloride and excess sodium hydroxide. And so the reaction here is magnesium chloride plus excess sodium hydroxide. And so what we're going to precipitate is magnesium hydroxide and sodium chloride. We're going to have 2 sodium chlorides. We need at least 2 sodium, so excess means we have more than 2 sodium hydroxides for this. This is a solid here. This is aqueous. Sometimes we leave off aqueous to save time. Aqueous here. And so what we have here is 25 milliliters of solution. So what we're going to do is we're going to go from 25.0 milliliters of solution to liters of solution. And then from liters of solution to moles of pure solute using the molarity. Moles of pure solute. And then we have moles of, oops, this is wrong. Yeah. That was magnesium hydroxide. Oh no, that was right, sorry. What am I doing? All right, then once we have moles of magnesium chloride, we're going to go to moles of magnesium hydroxide, and from moles of magnesium hydroxide, we'll go to grams of magnesium hydroxide. And that's just laying out the path for this. And so we're going to go from milliliters of solution to liters of solution. From liters of solution, we'll go to moles of pure magnesium chloride because they give us the molarity here. 0.398 moles of pure magnesium chloride per liter mixture or solution. And then from moles of pure magnesium chloride to moles of pure magnesium hydroxide using mole to mole conversion here from the balanced chemical equation. It's a 1-to-1 mole ratio. And then from moles to grams here, and we can calculate it. Let's look at another stoichiometry problem. Calculate the mass of calcium phosphate that will precipitate when excess sodium phosphate solution is added to 100 milliliters of 0.130 molar calcium nitrate. So we're going to take calcium nitrate. Calcium nitrate. Here. Calcium is 2 plus, nitrate is 1 minus, so CaNO3 2. Calcium nitrate. With excess sodium phosphate. So excess sodium phosphate. Sodium phosphate is Na3PO4. And this is going to produce calcium phosphate. So calcium phosphate, calcium is 2 plus, phosphate is 3 minus. So what we can do is we can go Ca3PO4 2. That is drop the 2 plus down here, the 3 minus over here. So Ca3PO4 2. This is a precipitate. The other product is going to be sodium nitrate. Now, we're going to need 3 calciums, so we'll need 3 calcium nitrates. We're going to need 2 phosphates, so we're going to need at least 2 sodium phosphates here. That's going to produce that, and that's going to give us 6 sodium nitrates out there. All right, calculate the mass when excess, okay, solution is added to 100. So this is not a limiting reagent problem. Actually, it is. This is the limiting reagent problem. That is, we already know what the limiting reagent is calcium nitrate. So we're going to go from 100.0 milliliters of solution to liters of solution. And then from liters of solution, we're going to go to moles of pure calcium nitrate using the molarity. The molarity is given here. And then over here to moles of calcium phosphate. It's a 3-to-1 mole ratio. And then moles to grams. There. There's a 0.130 moles per liter is the molarity that we're going to use over there. So let's take a look. And so they go from milliliters to liters of solution, to moles of pure calcium nitrate using the molarity 0.130 molar, which means 0.130 moles of pure calcium nitrate per liter of solution. The solution is a mixture. And then we had a 1 to 3 mole ratio here. 1 mole of calcium phosphate precipitated for every 3 moles of calcium nitrate reacted. And then once we got moles of calcium phosphate, we just need the molar mass. We can look that up or calculate ourselves, and we get 1.34 grams of calcium phosphate. $95. How many milliliters of 1.5 molar sodium hydroxide solution must react with aluminum to yield 2.00 liters of hydrogen? Measured at 22 degrees C and 789 torr by the reaction of this. All right. So this is a mix of solution volume and gas volume. So we have to be careful, because we got to make sure we know the difference between the solution volume and the gas volume here. And so we have 2.00 liters of hydrogen. Well, hydrogen is a gas. And so, here, 2.00 liters of H2 gas. This is not a solution. So if we have a gas, then we like to calculate the molar volume here. We can calculate the molar volume if we know the temperature and the pressure. So the molar volume is RT over P. And so let's go ahead and calculate it. And assume we're already pretty good at calculating these things. So R is 0.08206. T is 273, 295 divided by P, which is 789 torr, converting it to atmospheres by multiplying by 760, 23.317. 23.31 liters per mole. We're only allowed 2 sig figs. We're only allowed 2 sig figs here, so I'll carry some extras. So we're going to go from liters of hydrogen to moles of hydrogen. This is liters of pure hydrogen to moles of pure hydrogen using the molar volume here. And then from moles of pure hydrogen to moles of sodium hydroxide here using the mole ratio. It's a 6-to-3 mole ratio. And the moles of sodium hydroxide to liters of solution, liters of sodium hydroxide solution, using the molarity. Molarity is given here of 1.5 moles of pure sodium hydroxide per liter of solution. And so that should take us to where we need to go. So let's take a look at the answer here. So here, let's see what they're doing here. What the heck do they do here? I don't know what they're doing here. I do, but I don't understand why they're doing it, you know. This molar volume is weird. Well, anyway, since I don't really see exactly what they're doing here, I'm going to set it up myself. I mean, I don't understand why they're doing it the way they're doing it. I just do it like a standard stoichiometry problem. 2.00 liters of hydrogen gas. And then we have the molar volume here that we just calculated. And so we have 23.31 moles of gas per liter of gas. This is for gas at RT. It's for gas. And so that gives us moles of hydrogen gas. And then the mole ratio here, 6 moles of pure sodium hydroxide per 3 moles of hydrogen gas. And then the molarity, 1.5 molar. And so 1 liter of sodium hydroxide solution contains 1.50 moles of pure sodium hydroxide. And then they want milliliters, so let's convert it liters to milliliters, 1,000 milliliters per liter. And so this is the way I would have set it up here. And so I'm going to get 2 times 23.31 times 6 divided by 3 divided by 1.5 times 1,000. Okay, what did I do? Oops, I know what I did. Obviously I made a mistake because my number came out ridiculous, 186,000, and I see my mistake right here. It's 1 mole of gas is 23.31 liters. That's a molar volume. And so 23.31 liters per mole. This is what it is. And so let me recalculate it. It's 2 divided by 23.31 times 6 divided by 3 divided by 1.5 times 1,000. All right, I get 114.4 milliliters of sodium hydroxide solution. So I would have done it like this, and so I'm not exactly sure why they're doing it like that. But this is just your standard stoichiometry setup. What volume of 0.842 molar sodium hydroxide solution would react with 8.74 grams of sulfamic acid? This is sulfamic acid here, a solid acid with 1 replaceable hydrogen. So this is actually only a monoprotic acid. That's important to know. Actually, this is an amine type, you know, so this looks like the acidic hydrogen here. So this is what we call a monoprotic acid. Let's clear the drawing here. And so we need the balanced chemical equation. So So if we look at sulfamic acid, we just have one hydrogen on there to neutralize. So it's going to be NH2 SO3H. And so this must be the acidic hydrogen here on the end. Okay, plus sodium hydroxide. And so it's going to react in a 1-to-mole ratio because hydroxide only wants 1H plus. And so we're going to form this sodium salt of this NaNH2 SO3 plus water. 8.74 grams. This is a solid acid. So this is 8.74 grams of pure acid. 8.74 grams of acid. I'm just going all acid because it's, and then we need the molar mass. And so we just do gram to mole conversion, the molar mass. I can look up the molar mass on Wikipedia. And then we're after sodium hydroxide. So we'll go to moles of sodium hydroxide. It's a 1-to-1 mole ratio. And the moles of sodium hydroxide, we can go to liters of solution by using the molarity here, the molarity. And so let's see how they did it. So they put the sodium on the end. You could do that as well, you know, because the hydrogen is here. We can replace the hydrogen with the sodium ion at the end. And so that's often written like that as well. I wrote it in the front. And they wrote it at the end. So they have grams of pure acid to moles of pure acid using the molar mass. So we're going to look that up here, 9709. And then moles of pure acid to moles of sodium hydroxide. And moles of sodium hydroxide liters, or actually they went to milliliters, but here we could have gone to liters using the molarity, 0.842 moles per liter, and then convert it to milliliters, 107 milliliters. So this, I would have done it like this. So it's good. Let's look at the next one here. The equation for a reaction by which a solution of sodium carbonate may be standardized. Standardized just means figuring out what its composition is to a high degree of accuracy and precision. And so standard solutions have their compositions well defined, well known. And so we have this sodium carbonate here with this acid. Now, organic acids often have a common name. So this is some common to form this. This is metathesis for type reaction. The student determines that 5.038 grams of acid uses 51.89 milliliters of sodium carbonate solution in the titration. Find the molarity of sodium carbonate. All right, now titrations, we're after molarity usually. And so if we're after molarity, then we need to know what is the molarity of sodium carbonate. And so molarity of sodium carbonate is what we want. So what do we need in order to get the molarity of sodium carbonate? We need the moles of sodium carbonate divided by the liters of sodium carbonate solution. And then we figure out what we have. We have 51.89 milliliters of sodium carbonate solution. And so what we can do with that is we can just convert that to liters. And so this is equal to 0.05189 liters of sodium carbonate solution. Sodium carbonate solution. And so we want that on the bottom here. And so we need moles of sodium carbonate per liter. But we don't have a liter, we have 0.05189 liters of solution, which we'll put there, sodium carbonate solution. Now, how do we get moles of sodium carbonate? Well, we're given grams of acid. So what we're gonna have to do is we're gonna have to go from grams of acid to moles of acid, from moles of acid to moles of sodium carbonate. So what we're gonna do is we're just gonna use stoichiometry to get the top here. And so this is going to equal 5.038 grams of acid. And then we'll get the molar mass of this acid. The molar mass of this acid, I don't know the name of this acid offhand, so we'll have to calculate the molar mass. And so calculating molar mass, I have 6 hydrogens, that's 606, and then 7 carbons. 7 carbons is 7 times 1201. 8407. And then 2 oxygens. Well, 2 oxygens, 32. And so let's just add it up. This is going to be 0.13, and then 80, 111, 112, I think. Actually, I better just punch it in my calculator. 6 plus 84 plus 32. Less likely to make a mistake. 122, 13. And so mole of this acid weighs 122.13 grams. And so we go from grams of acid to moles of acid, and the moles of acid to moles of sodium carbonate, that's a 2-to-1 mole ratio. So 1 mole of sodium carbonate for every 2 moles of acid. And that's what we want on the top. We want, actually we don't, is that what we want? Yeah, we want the molarity. So that's moles over liters, 0.05189 liters of sodium carbonate solution. Sodium carbonate solution. And so this is going to come out to 5.0389. No, 5.038, sorry, 5.038 divided by 122.13 divided by 2 divided by 5189, equals. And so I get a molarity of 0.3974 molar sodium carbonate. Now, all the units should cancel out to give us moles per liter. So grams of acid, look at grams of acid cancel, moles of acid cancel, that leaves us moles of sodium carbonate over liters sodium carbonate solution. So that should be it. Let's check the book. 3976 versus 3974. It's molar mass is probably off. I had 121.213. They had 122.12. They also did round off here. I didn't do round off. I carried all the digits. Molar mass is just slightly different because of hydrogen, probably. I rounded hydrogen to 101. I rounded it to 101 to make the calculation faster than using 108. A student is to titrate maleic acid. Maleic acid is a common acid, and it has 4 hydrogens. 2 of these are acidic, 2 are non-acidic, so these 2 will react. These 2 are bonded to hydrogen, these 2 are bonded to carbon. So it gives it different reactivities. Hydrogens bonded to carbon are not acidic. With KOH. And so the equation for the reaction here, we can figure it out. Each hydroxide wants 1 hydrogen. So we have H2C4, H2O4. And so we're going to need, actually we're going to need 2 sodium hydroxides to react with this. And that's going to form sodium malate, which is C4H2O4. There's 2 sodiums are required for that, plus 2 waters. So driving force for this stronger acid, the weaker acid. So she dissolves 1.45 grams of maleic acid in water and titrates 50.0 milliliters of the base to neutralize the acid. What is the molarity of the KOH solution? So again, whenever we want molarity, then we set it up as a titration type problem. When I set this up as a titration problem, I set it up the same way. I just put molarity, we want the molarity of KOH. In order to have the molarity of the KOH, we need to know the moles of KOH divided by the liters of KOH solution. Okay, the liters of KOH solution is given 50 milliliters of base. Base is KOH. And so let's convert that to liters, moving through a decimal 3 over. So this would be 0.0500 liters. And so that gives us moles of KOH. Okay, now we have the liters. The liters is going to be 0.0500 liters of KOH solution. And so that's given. But the moles of KOH, we have to use stoichiometry to get that. And so in order to use stoichiometry, we're going to start off with 1.45 grams of maleic acid. So this is a solid acid, 1.4 grams of pure acid. And so we'll just go to moles of pure acid. And so on the top here, I want moles of KOH, but I don't have it. I'm starting off with acid. So we'll start off with 1.45 grams of acid, maleic acid. And then what's the molar mass of maleic acid? I could calculate it, but to save time, I'll just look it up here. The maleic acid is a very common acid, and it's used for different things. It has the different uses. What is it used for? A number of things. You can read through it here, but its molar mass is 116.07. We'll use that. And so we're going to go from grams of acid to moles of acid, and the moles of acid just to moles of KOH. Why did I write NaOH? This is KOH. This is potassium malate. And so moles of acid to moles of KOH, and then stop there. So grams of acid to moles of acid. This is 116 point, I forget that number here, 116.07, 116.07. I forgot that number because in the previous page it was a different number here. They had 116.1, so they had rounded it to 1 decimal place. I didn't want it to 1 decimal place. I wanted it to 2 decimal places. That's why I went back to that other page. And so it's 116.07 grams per mole of acid, maleic acid in this case. And then the mole ratio here is 2 moles of KOH for every 1 mole of maleic acid. So 2 moles of KOH for every 1 mole of acid. Okay, and so this is going to give me moles of KOH on the top, moles of pure KOH on the top divided by liters of KOH solution on the bottom, 0.0500 liters of KOH solution is going to give me what? Spill my coffee. Wipe that out. All right. It's going to give me, okay, 1.45 divided by 116.07 times 2 divided by 0.05. 0.4996. I'm allowed 3 sig figs, 0.4996 molar or 0.500 molar to 3 sig figs. Let's see what that comes out to. .500 molar. Okay. A student finds that 37.80 milliliters of 0.4052 molar sodium bicarbonate solution is required to titrate 20.00 milliliter sample of sulfuric acid solution. What is the molarity of the acid? So again, another titration problem. We got to figure out the molarity. This one, they gave us the equation here. So that's good. We don't have to figure it out. And so we want the molarity of the sulfuric acid. Get the molarity of the sulfuric acid. What do we need? Molarity of the acid, in this case, we need the moles of acid divided by the liters of acid solution. Okay, this is 20 milliliters of sulfuric acid solution. And so 20 milliliters is 0.0200, or this is going to be 0.02000 because we got 4 sig figs liters. And so we have the bottom as 0.02000 liters of acid solution that was used here. Problem is we don't have the moles of acid, but we can figure out the moles of sodium bicarbonate because we have the volume and the molarity. And so if we have 37.80 milliliters, we'll go to liters, and liters will go to moles using the molarity here, 0.4052 moles per liter. And then once we get moles of that, we can get moles of acid using the mole ratio here. And so we'll go 37.820 milliliters. I could convert that to liters here if I wanted to, because this is moving at 3 over. So it's 0.03780 liters. And so I'll just do that, 0.03780 liters of acid solution. And then we have the molarity here, which is 0.4052 moles of, oh, actually, this is not acid solution. This is base solution or bicarbonate. Bicarbonate's amphoteric. It could either act as an acid or base. Okay, so this is 0.3780 liters of bicarbonate solution. And so I'm going to call it just B. Bicarbonate solution. And then the molarity, 0.4052 moles of pure bicarbonate, so Bi, per liter of bicarbonate solution, per liter of bicarbonate solution. Okay, and then the mole ratio, it's a 1 to 2 mole ratio. So 1 mole of acid, in this case sulfuric acid, for every 2 moles of bicarbonate, pure bicarbonate, non-bicarbonate solution. And so that should give it to us here. And so that's going to be 0.0378 liters times 0.4052 moles per liter divided by 2. That gives us moles of acid divided by 0.02. 0.382. So I get 0.3829 molar sulfuric acid. Titrations are used to figure out an unknown concentration with a high degree of precision and accuracy. We're allowed 4 sig figs. So let me add one more. More sig figs is good because it's more precise. And so titrations, you usually end up with 4 sig figs at the end. Yeah, like here, 0.3829, 4 sig figs. Okay, the next series of questions deal with normality. We aren't dealing with normality here. Skip. Normality. In fact, this whole section deals with normality. Section 1613, skip that section. Now we're in 1614. Now we're on colligative properties here. Okay, so is the partial pressure exerted by one component of the gaseous mixture at a given temperature and volume a colligative property? Pressure, colligative property, gaseous mixture. Justify your answer. Colligative is, I don't know what they're talking about. In a way, yes. In a way, no. Partial pressure is a colligative property because it depends on the number of particles and is independent of their identity. All right, so I guess yes. Partial pressure would go down or up depending on how many particles you have. That makes sense. A student dissolves 27.2 grams of aniline in 1.20 times 10 squared grams of water. At what temperatures will the solution freeze and boil? And so what we need is, we need the equation for that, which I didn't give you the equation for that. I forgot to write it down. But it's called delta TF and delta TB. And so delta T, let's see, F is the change in the freezing point. And that's going to equal K sub F times the molality. Now this molality is the total solute. Total solute particles. It doesn't care what the particles are. It just wants to know how many total particles there are. This is a constant found in a table. So we look that up in a table. All right, and then we have a delta TB, which is the boiling point, and it's going to be KB times little m, the molality. And so that's a constant we find in the table. And so what is it for water? And so we got to look that up for water. It's got to be given. Well, we can look it up. So it's called the freezing point depression constant from water. 1.86 degrees C per mole. That's Kf. 1.86 degrees C per mole. So for water, this is only for water. For water, Kf equals 1.86 degrees C per mole. So let's go ahead and do the calculation for delta TF. Delta TF is 1.86 degrees C per mole. Now, how many mole do we have here? And so this is grams per gram of water. So we have grams, we have 27.2 grams of aniline. Per 120 grams of water, 120 grams of water. And so we need moles of aniline per kilogram of water. And so aniline, I don't want to calculate the molar mass, although it's not that hard of a calculation to get that molar mass, but I'm going to try to save some time here. Of course, if you don't know how to calculate these quickly, then you should get more practice. 9313. And so it's 9313 grams per mole. So what happened to, there it is. So 1 mole of aniline is 93.13 grams of aniline. And so here the grams cancel and leaves us with moles. Well, that's what we want for molality. We want moles on the top and then kilograms of solvent on the bottom. And so there are 1,000 grams per kilogram. And so we can calculate the molality here. It's going to be 27.2 divided by 120 divided by 93.13 times 1,000. Gives us 2.43. 2.43 sub 3 mole aniline. And so all we do is just multiply it by 2.43 sub 3 mole. So times 1.86. That's 4.527 degrees C. So the freezing point is going to equal the normal freezing point minus delta T sub B, or T sub F, sorry. And so the normal freezing point is 0 degrees minus 4.527 degrees C. And so, and this solution is going to freeze at minus 4.5. Many sig figs, 3 sig figs, minus 4.53 degrees C. That's the new freezing point of this. Okay, what temperature will this boil at? And so we'll need to find KB, the boiling point elevation constant. And so let me look that up. It should be in your book, but I didn't see it in your book for some reason. And so boiling point elevation. Boiling point elevation constant. 0.512 degrees C per molal. So 0.512 degrees C per molal. And so let's go ahead and calculate that here. And so KB is 0.512 degrees C per molal. So the more molal, the bigger the increase here. Times 2.433 molal. 2.433 molal, and what's that going to give us? So 0.512 times 2.433 equals 1.245 degrees C. And so the new boiling point is equal to the normal boiling point plus 1.245 degrees C. And so the normal boiling point is 100. And so this is going to boil at 101.245 degrees C, or 101.25 degrees C. So 101.25 degrees C will be its boiling point there. So those are boiling point elevation and freezing point depression calculation here. Okay, is it break time now? Kazra, is it break time now? What time did we end the last break? No, 30 at 30. Pretty soon will be break time. All right, let's see what we got here next. Questions. Aniline. Aniline is used in the polyurethane manufacturing process. Materials made from polyurethane include foams, spandex, hardwood floor coatings, dolly wheels, and many other end products. Calculate the freezing point of a solution of 2.12 grams of naphthalene, C10H8, and 32 grams of benzene, C6H6. So first we have to calculate the molality. The molality is going to be moles of naphthalene per kilogram of benzene. So we'll do that. So we calculate the moles of naphthalene per kilogram. So we'll put this number of moles per kilogram. So we'll change the grams to kilograms of benzene, and we get this molality. Once we have that molality, we have to look up KF for naphthalene. Well, actually, we don't have to look up KF for naphthalene because they give it to us. So I didn't have to search it on Google or in the book. So KF for naphthalene is 5.10 degrees C. So delta TF is KF times molality, that's 2.63. Now we need to know what the normal freezing point is. The normal freezing point of naphthalene, or benzene, actually here, this is benzene, sorry. The normal freezing point of benzene is 5.5 degrees C. And so it's gonna be 5.5 degrees C, the normal freezing point minus 2.63. The delta TB, and that gives us 2.87 degrees C. Benzene's a solvent, it makes sense. We're looking at the freezing point of the solvent here. What is the molality of a solution of an unknown solute in acetic acid if it freezes at 14.1 degrees C? The normal freezing point of acetic acid is 16.6 degrees C. So here we can calculate delta TF. Delta TF is going to be the difference here. So it's minus 2.5 degrees C. So it's 2.5 degrees C, delta TF is. And so if we know what delta TF is, then delta TF is equal to KF times M. So we can calculate for M. So first we get delta TF, 2.5 degrees C, and then calculate for M, because delta TF is equal to KF times M. So we just divide by KF and get 0.64 molal. A solution of 16.1 grams of an unknown solute in 600 grams of water boils at 100.28 degrees C. Find the molar mass of the solution. Now, this is an interesting application of determining molar mass and also a molecular mass as well, using colligative properties. And so a solution of 16.1 grams of unknown. So we want to find the molar mass of an unknown. What is the molar mass? The molar mass is equal to the grams of unknown per mole of unknown. So how many grams? Well, actually we have the number of grams. It's 16.1 grams of unknown. And so what we're missing is we're missing moles of unknown. And so this, how are we going to get the moles of unknown here? The grams is given here. Well, what other information do they give us? They give us that it boils. So they give us the boiling point. And so what we could do is we could figure out delta T sub B. Delta T sub B is 0.28 degrees C, because normally water boils at 100, and this is boiling at 100.28. So this is delta T sub B. Delta T sub B is equal to KB times little m. And so if we do that, let's see, KB, I know what KB is. All right, I know what KB is, so I can figure out little m. So KB is 1.86. Was it 1.86? Or 0.5? No, it was 0.512, sorry. 0.512. Freezing point was then 0.512 degrees C per little m times m. So we could solve for molality here. And so what is the molality? So the molality is going to be 0.28 divided by 0.512. It was 0.5. The molality is 0.5468. We're allowed to, this is too many sig figs, I'm allowed to a molal of the unknown. All right, but they tell us they tell us the grams of solvent. And so, so we can do this here. We can do this. We can go from this is 600 grams. Just go 600 grams of H2O. Then we're going to convert that to kilograms. And so a kilogram is equivalent to 1,000 grams. So now we have kilograms of H2O. And the molality is this. It's going to be 0.5468 moles of unknown per kilogram of solvent. The solvent's water. And so it's going to be per kilogram of water. In this case, this is dissolved in water. And so this is going to give us the moles that we can plug in here. And so what is it going to be? It's going to be 600. I didn't put it all in one equation. I could have. 600 divided by 1,000 times 0.5468. 0.5468. 0.328. And so this gives us, 0.3208 moles. And so we'll plug that in. So I'm just going to flip this over. and then times 16.1. And that gives me 49.07 grams per mole. I'm not allowed this many sig figs, but we'll round it later if need be. So that's essentially what they kind of did here. You can follow along. So they rounded it. Once you, actually, mine is off. They got 50 grams per mole. I got 49. Oh, I see what they did here. They rounded this. Here. They rounded this. They used 0.52. I used 0.512. They use 0.52. I use 0.512. This could be wrong. This is from Flexbooks. I got to be careful. It's 0.51. I have to be careful. I want to use reliable data. And so maybe on Wikipedia, or Purdue probably has reliable data. We look at Purdue. We look for KF on Purdue.
Professor?
Yes.
It's break time.
All right. Okay, it's break time. So let's break here. I'll stop. I'm going to pause the recording. I'm going to resume. All right. So their data is a little off from mine, and plus they have intermediate rounding here. Intermediate rounding is going to result in there. And they're using 0.52. So I looked it up on Purdue. Purdue University is using 0.512. So probably 0.512 is probably more up to date, I would think. But it's just slightly off, 50 versus 49. So let's go with it. All right, I need to finish this chapter, so let's go on here. When 12.4 grams of unknown solute is dissolved in 90 grams of phenol, the freezing point depression. Oh, so this is calculating molar mass again. So molar mass is going to be grams, 12.4 grams, and we just got to figure out the moles. So how did they figure out the moles? They used, first they figured out the molality based on delta TF and KF. They figure out the molality, and then from there they could figure out the moles using molality as a conversion factor. They have the grams. They give us the grams of solvent. We go to kilograms of solvent. So similar problem, except just using the freezing point. 129. The normal freezing point of an unknown solvent is 28.7 degrees C. A solution of 11.4 grams of ethanol. The molal freezing point. What is the molal freezing point constant? So this one we want to solve for KF, and so. We solve for KF, so we need the moles, we need the molality. So here in the first steps, they're figuring out the molality. Once they figure out the molality, they can solve for the KF if we know what delta TF is. And we know what delta TF is because we see the change in the freezing point here. The delta TF there. So just solving for different things. And then these are just some, like true or false. Let me skip some of these. True, false ones, because there's explanations there. Percentage concentration by mass does not depend on temperature. That's an advantage of it, as masses don't change with temperature. Let's look at the challenging problems. Suggest a way to separate two miscible liquids. Do you know of any widespread industrial process in which is done? Distillation. Distillation is one way to separate it. Distillation. And distillation is used to separate crude oil into gasoline and kerosene, etc. The text gives no explanation of forces that must be overcome during the dissolving process. Can you imagine what the forces might be? The forces that must be overcome are, attraction between solute particles and attraction between solid. They did talk about that. We had to break that. That was in one of the slides. Silver acetate has a solubility of 2.52 grams per 100 grams of water. So this would be considered soluble at 80 degrees C and 1.02 grams per 100 grams at 20 degrees C. How do you prepare a supersaturated solution of silver acetate? Well, acetates have trouble nucleating because of their trigonal planar shape. They're kind of weird shape, they're hard to pack. And so you heat it up to 80 degrees C, you dissolve 2.5 grams, and then you slowly cool it to 20 degrees C. Hopefully when you cool it, it doesn't crystallize. If it precipitates, forget it. But if you have very clean glassware, there's no dust, there's no scratches or nicks in the glassware, then what can happen is it won't nucleate, won't crystallize. And then cool it without disturbance, you know. You're trying to prevent nucleation, basically. 140, consider a sample of pure sugar that has been finely powdered. What advantage does it have over granular? Well, we can buy both, pure sugar powdered or pure sugar granular. Granular is big crystals, powdered is tiny crystals. Much more surface area in powdered, so powdered reacts a lot faster. For sweetening coffee, powdered sugars will dissolve a lot faster. More surface area dissolves more quickly. The density, it also reacts much quicker. Powdered sugar results in explosions. I mean, we had that explosion with ammonium nitrate, but you gotta watch out for powdered sugar and powdered flour. Let's see, powdered sugar explosions have killed people because sugar is a good fuel and oxygen in air is a good oxidizer. And so let's take a look. Imperial sugar dust explosion. So this is powdered sugar dust. Look at the damage here. This is the Imperial Sugar Company in Georgia. 14 people were killed, 36 injured in a sugar dust explosion. And so if you are interested, this is just one of many. There's sugar and silo. That's the 14, that's the same one in front of, you know, you have this, in bakeries it happens, you know, in bakeries, they have powdered sugar and powdered flour explosions. And so you gotta watch out. You just need heat and you need a powdered sugar, you know, filling up the room. You got air in the room, you just need an ignition source and then you get an explosion. There have been lots of demos of that too. Let's see, powdered sugar explosion. Where was that? This is only 26 seconds. You have to aerosolize it, you know, make a fine aerosol of powdered sugar. Okay, come on, this is 26 seconds. Where's the explosion? Oh, there we go. That was just sugar and air. Okay, I need to pause this. Okay. The density of 18.0% HCl is 1.09. Calculate molarity. This is a common calculation. And so we're going from percent by mass to molarity. And so this is just dimensional analysis. And let's just set it up really quick. And so we're going to have 18 grams per 100 grams. And so this is 18.0 grams of pure HCl per 100 grams of HCl solution or mixture. And so these are two different things. And then what we'll do is we'll convert the top into moles. So convert the top into moles. And then the bottom, we're going to convert into milliliters first using the density here. 1.09 grams of solution per milliliter of solution, HCl solution, and then from milliliters to liters. So it's just a dimensional analysis problem. And so convert the top into moles and the bottom into liters. And so grams to milliliters using the density and then milliliters to liters. Okay. Methyl ethyl ketone is a solvent popularly known as MEK, that is used in cement plastics. How many grams of MEK must be dissolved in 100 milliliters of benzene to yield a 0.254 mole solution? So this is very similar to calculations we were doing earlier. We did lots of molality calculations, so I'm going to skip this one. Calculate the mass of, this is oxalic acid dihydrate required to make 250 milliliters 0.500 normal. This is normality, skip that. The iron 3 ion content of a solution may be found by precipitating it as iron 3 hydroxide and then decomposing the iron 3 hydroxide to iron 3 oxide by heat. How many grams of iron 3 oxide can be collected from 35.0 milliliters of 0.516 molar iron 3 nitrate? And so this is a multi-step. When we have a multi-step like this, then this is the way we handle this multi-step thing. So we're going to have iron 3 nitrate. And so I can even make this even faster, more compact, but I'm going to do iron 3 nitrate. And then we're going to precipitate it as a hydroxide. So we'll need 3 sodium hydroxides because we're going to form iron 3 hydroxide. 3 hydroxide like that. So this is going to be a 1-to-1 mole ratio here, plus sodium nitrate, so plus 3 sodium nitrates here. And then the next step is we're going to decompose this. And so this is going to form iron 3 oxide. And so they don't give us the details of this, but it's a Lewis acid-base reaction, Fe2O3 plus, etc. It's actually, you can kind of figure it out. It's going to form Fe2O3 in water. And so we're going to have this 1/2 to get this, or we double everything. It's probably easiest to double everything here. And so let me get rid of that 1/2 here. And so when a hydroxide gets converted into oxide, we lose water, but I'm not going to do it. And so we're going to double everything. 2, 6, 2, 6, and then this remains 1. So we got 2 irons here going there. And so this is all the stoichiometry we need. We don't need to balance everything because all the iron that started off here ends up here. And so we didn't lose any iron anywhere else. And so it's a 2-to-1 mole ratio. And so what we're going to do is we're going to go from, where are we here? We're going to go from milliliters of solution. So we get milliliters of solution to liters of solution. And then we have the molarity. And so if we have the molarity, we can go from liters of solution to moles of iron 3 nitrate. And then from moles of iron 3 nitrate to moles of rust, iron oxide. And then from moles of rust to grams of rust here. So this is the stoichiometry set up here. Let's see what they did. So they went from milliliters solution to liters solution, liters solution to moles of iron 3 nitrate, moles of iron 3 nitrate to moles of iron 3 oxide. Even though it's a 2-step reaction, all the iron ends up there. And then to grams using the molar mass. So that's what they did there. Let's go to 146 here. A student adds 25 milliliters of 0.350 molar sodium hydroxide to 45.0 milliliters of 0.125 molar copper 2 sulfate. How many grams of copper 2 hydroxide will precipitate? This is a limiting reagent problem. And so a limiting reagent problem, we have to do 2 stoichiometry calculations and pick the smaller amount. And so one, we do a stoichiometry calculation with the sodium hydroxide to figure out the yield of copper 2 hydroxide. And then this is calculation 1. Calculation 2 is we'll do it based on this to figure out the yield of copper 2 hydroxide. So we figure out the yield of copper 2 hydroxide from calculation 1 and then figure out from calculation 2 and pick the smaller amount. The smaller amount's the limiting reagent and the small amount is the theoretical yield. And so that's what we're looking at for this particular problem. And so we pick the smaller amount. So first we figure out how much is going to come from the sodium hydroxide. So go from milliliters solution to liters solution to moles of sodium hydroxide, moles of sodium hydroxide to moles of copper 2 hydroxide to grams of copper 2 hydroxide. It was 0.427 grams. And then we do calculation number 2 from the 45 milliliters of copper 2 sulfate. For 45 milliliters of solution to liters of solution to moles of copper 2 sulfate, moles of copper 2 sulfate to moles of copper 2 hydroxide to grams, and it comes out to 0.549 grams. And so this is the smaller amount. That's the theoretical yield, 0.427 grams will precipitate, and this is the limiting reagent. We have excess of the copper 2. So this is a limiting reactant problem using solution chemistry. And so a little bit more steps involved there, but not much. Okay, let's look at the next one here. Next one is an analytical procedure for finding the chloride ion concentration in a solution involves precipitation of silver chloride. So we could have titration involving precipitation as well. What is the molarity of the chloride ion if 16.80 milliliters is needed to precipitate in a 25 milliliter sample of the unknown? Okay, so this is very similar to the titration problem that we looked at. And so we're trying to figure out the molarity of, what is the molarity of chloride? And so the molarity of the chloride ion. All right, so this is a little bit trickier though, is needed to precipitate. Okay, so the chloride is in a 25 milliliter sample. And so molarity is we need the moles of chloride per liter of chloride solution. So the liters of chloride solution, well, let's convert that to 0.02500 liters of chloride solution. This is the chloride solution. So we have the denominator. And so all we need to do is we need to figure out the moles of chloride from stoichiometry because we have the 0.02500 liters of chloride solution in the denominator. And so how are we going to get the chloride from the stoichiometry of this? Well, this is stoichiometry using a net ionic equation. And so we could do that here. Using a net ionic equation is fine here. And so what we're going to have is 16.80 milliliters of 0.629 molar silver nitrate, the source of silver ion. And so silver nitrate is AgNO3. AgNO3, nitrate salts are soluble. So that's AgNO3AQ. And soluble salts are strong electrolytes. So for every mole of silver nitrate, I have 1 mole of silver and 1 mole of nitrate. And so this is the way we do this one here. We're going to start off with 16.80 milliliters of silver nitrate solution. And then we're going to go to liters of silver nitrate solution. And then we're going to go to moles of silver nitrate. And then moles of silver nitrate to moles of silver ions. For every mole of silver nitrate that dissolves, we form 1 mole of silver ions. So it's a 1-to-1 mole ratio here. And so the mole ratio here is 1-to-1, so we can figure out, you know, it's the same thing, but we should show it as a step here. Okay, once we have the moles of silver ion, then we can figure out the moles of chloride ion. It's also a 1-to-1 mole ratio. And so we're going to go from moles of silver to moles of chloride. It's 1-to-1, and then we can plug that in here. And so once we get the moles of chloride, we'll plug that into the numerator, and that will be the answer once we punch the calculator out. And so here, they're going from milliliters of silver nitrate to liters of silver nitrate solution to moles of pure silver nitrate. For moles of pure silver nitrate, they should go to moles. I would have done more steps here, because just to make it a logical progression. I would have went from moles of silver nitrate to moles of silver ions. And so we know that we get 1 mole of silver ion for every mole of silver nitrate that dissolves. And then I would use the balanced chemical equation up here and said that we get 1 mole of chloride ion for every 1 mole of silver ion that reacts. And then I would have added this. What they did was they combined these two into 1 and then divided by the 0.025 liters. To get the molarity. That's the molarity of the chloride we have there. Okay, we have another minute, so let me see. Shoot. Needed to finish this chapter here, but I'm not going to finish it. So I got 150, 151, 152. Some of these. We'll have to finish on Monday since we're out of time. So I'm out of time. So that means we'll finish 16, not much left to finish on 16. We'll finish 16 on Monday. 17's acid base is pretty short chapter. 18's equilibrium. We aren't going to cover the whole chapter. It's pretty long. We're just going to hit the main topics on equilibrium and kinetics. And then 19 is going to be fairly short because it's just looking at batteries. We've already done the redox reaction, so we've already done part of it. Yeah, go, Moniza, go ahead, send that in. It's not a problem if you want to. I think since I haven't finished those yet. So if you notice something, you can do that if you want. Okay, that's it. So I'll see you guys on tomorrow. Tomorrow's a lab day. Actually, let me finish this during the lab. Let me finish this at the start of tomorrow. And then that way I can knock this chapter out this week, which would be better. And then next week we'll just have 17, 18, and 19 covered. Okay, so tomorrow we're doing a couple of labs, titration lab and chemical reactions lab tomorrow. And so we'll be doing that from school. All right, any questions or end things? The other labs, all the labs are going to be due like a week after, you know, a week after we complete it. So we haven't completed the chemical reactions, but what lab have we completed so far? We completed, did we complete we completed the Charles Law. So officially Charles Law is due tomorrow, but maybe I'll talk about Charles Law at the beginning too. There's a graph there. Maybe we'll do the graph together. That's probably a good idea. Officially Charles Law is due tomorrow. And the reactions, we still have to look at some of those reactions. The flame, you know, the Bunsen burner is already due. The measurement lab is due. So measurement should be completed for tomorrow. Okay. All right, any other questions? So measurements you should do, and the Charles Law, if you don't have it done, we're going to finish up the graph for Charles Law tomorrow. I want to show how I want the graphs. Okay, any other questions? Okay, if no other questions, I'm going to stop recording and